So this is Kinematics Part 2, still dealing with 1D motion. Now we're going to look at instantaneous velocity. Instantaneous velocity, very basically, is a specific point along that traveling. You're going to determine it by drawing a line tangent to the slope. And then divide meters per second to get the velocity at that specific point in time. So here's an example of what they did for that. All right. Sample problem, looking at average velocity and displacement. So let's use the guess method on this. First given that we come across is an average velocity. And it says to the east, so it's a positive 6.02 meters per second. And we also see a time of 137 seconds. And you're trying to calculate your displacement. How far did she travel within this time, noticing that you want meters because velocity was meters per second. So our original equation that I taught you was VF equals delta x over delta t. We want to multiply by delta t on both sides so that delta x is now isolated, the variable that you're trying to solve for. So in your calculators, please get your calculators out, guys. Don't just sit here and let the starter do the work for you. So in your calculators, iPads, cell phones, whatever, calculate 6.02 times 137. Get a calculator answer, 6.02 times 137. The calculator answer you should be seeing is 824.72. Always write down that calculator answer. That's the last part of the first S. Okay, so now going back to our givens here. We have three sig figs that we want in our final answer. So what does the 7 do to the 4, guys? Does the 7 round the 4 up or does it keep it the same? The 7 should round the 4 up. So therefore our final answer is 825 meters equals delta x. Okay, acceleration. Definition here is rate of change of velocity with respect to time. Rate of change of velocity with respect to time. The equation that I'd like you to use is AF equals the change in velocity or the change in time. But what if they don't give you delta? Then you're going to use VF minus VI over delta T. Usually that T is not going to break apart, but I think you're pretty comfortable with the idea that delta means final minus initial. So you might have TF minus TI, but odds are they're not going to ask you that. So I'm not going to break down VF and VI, but delta V, this would be your velocity, change in velocity more specifically, which would be measured in meters per second. Your delta T is your time, which is measured in seconds. So you get rid of your seconds here, the variable that you were left with, or sorry, not get rid of them. They're both in the denominator there. So what you're left with is your average acceleration, which will be measured in meters per second squared. So stop and think about this. Would acceleration be a vector quantity showing both magnitude and direction, or would acceleration be a scalar quantity showing only magnitude? Well, the easy way to assess this is check out the variables that are in that equation. Looking at velocity, is velocity a vector quantity or a scalar quantity? Velocity is a vector quantity, so therefore, so is acceleration. Velocity and acceleration. What we're looking at here is positives and negatives. So an object that has a constant velocity that would have the cruise control set, put yourself in the driver's seat. Are you touching the accelerator? Are you touching the brake pedals if you have the cruise control set? No, you're not touching any anything. So are you accelerating? No, you are not accelerating. So therefore, acceleration equals 0 meters per second squared. Okay, so what if you're increasing your velocity? If you are increasing your velocity, you would have a positive acceleration. That positive acceleration may imply that you are speeding up. Okay, you really only want to use the word speeding up and slowing down with acceleration, not with velocity. But I don't want to get too far into this because technically, if you are increasing your velocity in the negative direction, then you have a negative acceleration because that would be a positive and a negative. But if you are decreasing your velocity in the negative direction, then you have a positive acceleration. So two negatives would give a positive. There's a slide that you're going to see here in a second that will help this make more sense. Okay, if an object is at rest, then obviously you have no acceleration, therefore 0 meters per second squared. So check this out. If an object slows down, is the velocity a positive or negative value? If the object slows down, what's your speedometer doing? Is it decreasing? Are you decreasing your velocity or are you increasing your velocity? So it should be a negative value. What about your acceleration though? You're still like using a pedal, right? So that acceleration is going to be, sorry guys, that came out wrong. Positive value because you still have positive numbers. You haven't turned around yet. Remember, the only time that you have a change in the velocity is when you turn around. Well, that's from your kinematic curves notes. When you cross over on a velocity time graph, when you cross over the x-axis, that means that you change directions. So if you never crossed over the x-axis, then you would still have a positive velocity, but you would have a negative acceleration. Positive velocity, that is slowing down, so a positive and a negative would give you a negative acceleration. Okay, fabulous chart here. Signs for acceleration, like dog ear this one, highlight this one, do whatever you need. See what I mean about like you're going to have an object that has a positive velocity that is speeding up, that'll give you a positive acceleration. If you have an object that has a negative velocity and is speeding up, that's going to give you a negative acceleration. But if you have a positive velocity and it's slowing down, that's going to be a negative. So see how they're looking at two signs to figure out if it is a positive or negative acceleration. So that's kind of what I want you to assess when you're reading these problems. Make sure you're checking the direction as well as what the sign of the magnitude is that you're dealing with. Okay, so it says if I am moving to the left and speeding up, do you have a positive or negative acceleration? Well, left is negative and speeding up is positive. So a negative and a positive would give you a negative acceleration for your final answer. All right, determine the sign of velocity and acceleration at points A, B, C on the following graph. So let's kind of pretend like we are driving in a car right now. So we're going to break this into 3 different sections here. Okay, so let's say at this part right here, you are clearly speeding up, right? Your velocity numbers are increasing, and they're increasing a lot in a short amount of time. Agreed? So let's say that this is like an entrance ramp to the highway. All right, now look at part B, your velocity. It's staying pretty constant throughout, right? So let's say that this is a point while you're on your trip that you know you're going to be driving here for a little while, so you turn on the cruise control. Oh, look, here's my exit. So you are slowing down, but still in the positive direction, agreed? Because you haven't crossed over the x-axis. So your velocity is going from like, I don't know, from like 50 to 40 to 30 to 20 to 10 to 5, etc., etc. So on this one, this is the exit ramp. Clearly you slow down on exit ramps. You're not trying to speed up and make it through that light at the end, guys. Okay, anyways, back to this. So for part A, what I would like you to jot down is that you would have a positive acceleration, and that positive acceleration would give you a positive velocity. You're still in the positive direction, makes sense? Okay, so for part B, since you have a constant velocity, at 12:34 you're heading 65 miles per hour, at 12:35, 65 miles per hour, 12:36, 65 miles per hour. So you have your cruise control set. If you have your cruise control set, then you have an acceleration of 0 meters per second squared because you're not touching the accelerator or the braking system at all. And then part C, see you're trying to slow down. So you're decreasing your velocity, but you haven't changed directions. Since you haven't changed directions, it still stays a positive v, but now your acceleration is 0 because you have a positive velocity and you are slowing down. Since you are slowing down, then that is going to give you a negative acceleration. Make sense? Positive, negative acceleration. All right, moving right along. Sample problem on average acceleration here. This problem says that a startup bus slows down with an average acceleration of negative 1.8 meters per second squared. Calculate how long it takes the bus to slow from 9 meters per second to a complete stop. Ooh, complete stop. There's a given there. Please don't always think that givens are going to be given to you in the numeric form. Sometimes they'll be written out as well. So I see an acceleration, more specifically an average acceleration, of negative 1.8 meters per second squared. We also see that we have an initial velocity of 9.0 meters per second, and we have a final velocity of 0 meters per second. We are trying to figure out how long it will take. What unit do you want on time here? Checking it out, you want seconds. The original equation that I gave you is A average equals delta V over delta T. But look guys, look at your givens. You don't have a delta V, but you do have a final velocity and an initial velocity. So this is the equation that you really want to use. Okay, so now plugging in, we have to first rearrange the equation. So right now we're looking at A average equals VF minus VI divided by delta T. Delta T is what we want to isolate. So I'm just going to flip these two. I'm going to multiply by delta T on both sides. I'm going to divide by A average on both sides. So in other words, delta T equals VF minus VI all over A average. Plugging in then, that gives you 0 minus 9.0 divided by a negative 1.8. So 0 minus 9.0 is negative 9.0 divided by a negative 1.8. Please put that in your calculators. 9.0 divided by 1.8. And I left the negatives out because clearly it's going to be a negative number. So putting that in your calculator, 9 divided by 1.8, what do you see? Write it down. 5.0 is what you should see on your calculator. Okay, looking at your givens here, the least number of sig figs is 2 sig figs. We don't have a third one to try to do a comparison against. So your final answer is that it took 5.0 seconds for this bus to come to rest. All right, motion with a constant acceleration. This is when displacement is increasing per equal time intervals, thus you see an acceleration. So example, you're pushing down on the accelerator of your car. You're going to see a graph like this. If you see a graph like that, this is your stacks right here, guys. So if you see a position time graph or a displacement time graph that looks like this, the next thing you should see is your velocity time graph, and your velocity time graph will show a simple direct relationship. And if you're showing that, then that means that you had a constant acceleration throughout that travel. So there's your stacks of curves right there. Here's another instance. See how, this is time-lapse photography. So see how the time is, the distance is increasing as time between each of these is staying constant. So there's another example of showing a direct by the square, i.e. displacement time graph. Okay, so we're going to stop right there and actually do the kinematics as in one big slide and your free fall as in one big slide or one big video. So we're going to stop right here for this video.